then we're going to talk about units. Units are really, really important. I like this story. It's tragic, but, nobody died, so that's good, I guess. 1999, NASA lost the $125 million Mars Climate Orbiter due to a miscommunication over units. So they sent this thing up, and it was supposed to orbit around Mars and collect data and take pictures and stuff. So it gets up there, and they realize that the trajectory is not quite right. They need to make some adjustments. Well, the software on the orbiter was programmed to use metric units. And the guys down in Houston or wherever were doing their calculation using English units. So they come up with the adjustment, and they punch it into the computer, disregarding the units, and as a result, it got too close to the surface, and it crashed. Units are very important. Now, the good news is, errors that you make in units are not going to be this costly, right? So that's good, right? The stakes are much lower, but they could cause you to get an answer wrong on an exam. And you do that several times, and that could affect your letter grade in the course, right? So we're going to learn about units, and we need to pay attention to them. Have you ever thought about where units come from? Who decided how long an inch was? Yeah, originally, a lot of these things had to do with body parts. So a foot was defined by the length of the King of England's foot. Yeah, what happens when you get a very petite king, right? Does the size of the unit change significantly? That could be kind of awkward, right? Mess everything up. It's a little strange to think about, but all units are made up. Humans made them up, right? So there's a lot of them. We will deal mostly with the metric system and the English system. The only reason we're going to deal with the English system at all is because that's what we use in the United States. We talk about miles and inches and gallons and garbage like that, right? And we just can't seem to pull ourselves away from it. The English don't use it anymore, but we do. And we're independent from, I don't know, it's very strange. The metric system is what most of the world uses, and it's what we use in science. So if you have a choice between units, the rulers that you have in your drawers have inches on one side and centimeters on the other. When you have a choice, always choose the metric unit. Always, always, always. Technically, what scientists use is called the International System of Units, or the SI system. It has extremely subtle differences from the metric system, mostly to do with what the base unit is. So in practicality, the differences do not matter at all, and I'm going to completely ignore them. So these are base units in the SI system. Some of these we'll run into, the last two we won't. We'll see length, meters, mass, kilogram. Time is in seconds, that's the same as English. Temperature in kelvins, amount of substance is measured in moles. And then these last two, electric current and luminous intensity, we don't get into those in chemistry at all. But they are base units, so there they are on the list. So for length, we use meter. The abbreviation is a lowercase m. Those abbreviations are case sensitive, and we are very, very picky about them because the M in various forms gets used for lots of different things. So much like an email address or a case sensitive password, you get one digit wrong and it's wrong, right? You don't get into your account if you forget to capitalize the M. So meter is a lowercase m. It's important to have an idea of how long a meter is. So this is a meter stick. It's got centimeters on this side, so it's 1 meter long. And then on the other side, it looks like a yardstick, but it's actually a little longer than a yard because it's about 39 inches long. So a meter is like a yard. So if you do a calculation and find out that this person in the calculation is 5 meters tall, could that be correct? No, because a meter is like a yard. Is anyone 5 yards tall? That's 15 feet. No, that's like twice as tall as a really tall human. So we need to have an idea of how big these units are. Mass is measured with kilograms. So mass is slightly different than weight. Weight is the force of gravity on an object. Mass is the quantity of matter in an object. So if you weigh 130 pounds on the Earth and you travel to the moon and stand on a scale, the scale would say 21.5 pounds. Ooh, that's quite a weight loss, right? Does that mean you're really, really thin? No, you are the same size. But you're on a different, it's not a planet, but a different thing with different gravity, and so the force of gravity on you is much less. Anyone planning to leave the planet this semester? Didn't think so. If we're on the planet, we can use these words interchangeably. There are very slight differences in the force of gravity in different areas, but not significant. Nothing we have to worry about. So how big is a kilogram? A kilogram is roughly 2 pounds. Okay? In chemistry, a kilogram, 2 pounds, that's a bit much for us. We're not going to weigh out 2 pounds of calcium carbonate or something and put it in a beaker. It wouldn't fit. So we use the gram. To have an idea of how big a gram is, a nickel is 5 cents. A nickel weighs about 5 grams. So 5 grams, that's a small quantity of matter, but it's large enough that you can see it and handle it. We'll talk more about these relationships here. A gram is 1/1000th of a kilogram, or we can say that a kilogram is 1,000 grams. We'll talk about that when we get to the metric prefixes. Second is the measure of time. All of these units have very, very particular definitions, and if you're interested in them, they're in your textbook. One of them was recently redefined, which is, kind of surprising in the scientific world, but we're all familiar with what a second is. Temperature, the SI unit is Kelvin. Again, Kelvin is temperature is a measure of average kinetic energy of the particles that compose the matter. And this is not the moving through space type of kinetic energy, but the moving in place type of kinetic energy, how wiggly the matter is. Temperature determines the direction of thermal energy transfer. So here in my cup, I have an energy drink and some ice. And originally the energy drink was at room temperature and the ice was somewhere below 0 in the freezer. When I put these two together, we all know what happens, right? The energy drink gets colder, the ice begins to melt, and eventually they'll come to the same temperature. It never, ever happens that the energy drink gets hotter and more ice forms, right? That's just against nature. So temperature determines that the thermal energy, the heat, is going to flow from the warmer object into the colder object. So the English temperature scale is the Fahrenheit scale. There's a lot of stuff you can find online about the origins of these, and I'm going to resist talking about that because it took too long yesterday. The Fahrenheit scale has water freezing at 32 and boiling at 212 as a classic English unit where you just got these like random numbers, right? So the metric system uses the Celsius scale. This is based on the freezing and boiling points of pure water. So water freezes at 0 and boils at 100 degrees Celsius. So within that change, this is the same difference in temperature, but it's 100 degrees on the Celsius scale and it's 180 degrees on the Fahrenheit scale. So that makes that, and the fact that 0 is in a different place, makes temperature conversions very different from all of the other unit conversions that we're going to study. On both of these scales, it's possible to have negative temperatures. You get into mathematical equations and graphing things, and having 0 in your equation as a variable or negatives can cause some problems. And so the Kelvin scale gets rid of that issue. So the Kelvin or absolute scale there are no negative temperatures. This is accomplished by assigning 0 to the coldest possible temperature. It's a theoretical temperature. It's called absolute 0. How do we know what that would be? Well, at absolute 0, the motion of all the particles in the matter at that temperature would stop. So that would be, absolute 0 for students. We wouldn't be breathing, our hearts wouldn't be pumping, we would just literally be frozen. Nothing moving at all. Okay? You can't get any colder than that. Temperature is average kinetic energy. If nothing's moving, you can't have less kinetic energy than nothing moving, right? So 0 on the Kelvin scale is way, way down here. So based on that, water freezes at 273 Kelvin, and Kelvin is just the unit, it's not degree Kelvin like the other two. So it freezes at 273, and it boils at 373. So the difference in temperature between water boiling and freezing is still 100 divisions. And so that means that a Celsius degree and a Kelvin unit are the same size. They differ in where 0 is. So conversions with temperature units are done using equations. And these are the two equations. I will give these to you with your periodic table on the exam, because I know that Celsius Fahrenheit one's a little tricky to remember, but you need to know how to use these equations. So the way this works is, if you want the Celsius temperature, you take the Fahrenheit temperature, you subtract 32, make sure you finish that subtraction before dividing by 1.8. Kelvin temperature is the Celsius temperature plus 273.15. Sometimes we get a little sloppy and leave off the 0.15. Your book does that, and so I'm going to go along with it, but I don't like it. It's always okay to put the 0.15 on there. So let's do an example. Gallium's a solid metal at room temperature, but will melt to a liquid in your hand. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on A, the Celsius scale, and B, the Kelvin scale? So I think this is our first example of what is currently called a word problem. Right? When I was growing up, we called these story problems, and I think that's friendlier, right? It's a story. So the story problem. There's people who get story problems, and there's people who just do not get story problems. You either are like pretty good with them, or you hate them, right? And you know which kind of person you are. It has nothing to do with your intelligence or your determination or your work ethic or anything. It's just how your brain was made. It's how you think. But everyone can become better at doing story problems, okay? And if you want to pass this class, you're going to have to do a lot of story problems. And so I'm going to do my best to teach you how to become better at solving them. And if you need extra help out of what I'm giving you in lecture, please ask me. I just can't, spend all day doing story problems. So, important first thing is read the whole story. Next is numbers are generally important. And so we'll pull out the numbers and ask ourselves what those mean. And if there are units involved, we want to include those. So there's only one number in this problem, 85.6 degrees Fahrenheit. And then we're going to ask ourselves, what am I trying to find? And that often involves a question mark or a question word. Here we're looking for the temperature on the Celsius scale and the Kelvin scale. So I need to convert this from Fahrenheit to Celsius for part A. And for part B, I need to go Celsius to Kelvin. Well, actually, let me back that up. We're going to take this 85.6 degrees Fahrenheit and in some way get it into Kelvin. Temperature conversions, we need equations. So I don't expect that you have memorized those. So I'll write it down up here. So we need those equations. So to convert Fahrenheit into Celsius, I'm going to use this first equation. And it's nice, I don't actually have to rearrange it. If I was given Celsius and asked for Fahrenheit, then I would have to rearrange this equation. But I don't need to do that. I encourage you to always show your work. There's lots of reasons for that. What do I mean by showing your work? Write down the equation, plug the numbers in and write that down, and then write down your answers. So I'll be demonstrating what I mean by show your work. So the equation we're using is this. And to calculate the temperature, we're going to plug our Fahrenheit temperature in there. And get out your calculator if you don't have it out yet. You should always bring your calculator. There will be days we don't use it, but it's small. You can carry it around anyway. So I'm going to do this on my calculator, and I need at least one of you to do it on your calculator, because I think we all recognize that it's very easy to push a button wrong and make a mistake. So when you're doing, especially for an exam, but even homework, you do the calculation, you should do it twice. And if you get the same answer, it's probably good. If you get two different answers, they can't both be correct, right? So do it a third time and go for best 2 out of 3. So in class, I do it once, and one of you does it once, and then if I got it wrong, you need to call me on that, because I screwed up yesterday. Pretty much every day, actually. So we have to be careful with the order of operations there and make sure we tell our calculator exactly what we mean. You can put parentheses around like it's listed on the screen there, or 85.6 minus 32. Press the equal sign. That'll force it to finish the subtraction and then divide by 1.8. And so what my calculator is giving me is a lot of digits. And later this morning, we're going to learn how to decide, in general, how many of those digits to keep. And the unit is degrees Celsius. So significant figures are what we use to decide where do I round that. For temperature conversions, though, we can actually do it much more simply. It gives actually a better result than significant figures. So this is the rule for temperature conversions. Look at the starting temperature. What decimal place does it end in? Here, this ends in the tenths. So that means I want to round my answer to the tenths. So same number of decimal places, so I'm going to record that answer as 29.8 degrees Celsius. Yes?
Can we just put like a line on top of this one?
Yes. So this could be written as 29.7 repeating. And that's fine as well. But then we do need to round it appropriately. And so, yeah, you can use that in between if you need to. It doesn't come up very often, but sometimes it does.
Isn't the line on the second forever?
Yes. Good question. The 7 means it repeats forever. Why does this have an 8 at the end? Because my calculator can only show me so many digits. And so when it comes to the last one, it can show me, it looks at the next one and says, do I round up or down? And because the next one is also a 7, it rounds up to an 8. Any questions? So that's part A. We're also supposed to convert that temperature into Kelvin. I didn't give you an equation relating Fahrenheit and Kelvin. You could come up with one, but it's almost never needed, and so I don't even know what it is. So how do we do that? Well, first we convert to Celsius, and then we convert to Kelvin. And here that's pretty easy because we already did the Celsius conversion. So over here, we're going to take that Celsius temperature, 29.777, etc., and we're going to go to Kelvin. So Kelvin temperature is the Celsius temperature plus 273.15. And so this is giving me 302.9277, again, with the repeating business. Did I do the math right? The rule for rounding applies here as well. My original value had extended into the first decimal place, so I want to round this number to the first decimal place. And so we're going to call that 302.9 Kelvin. Any questions? Look, we got the answers right. Yes?
I wanted to make sure. So if the question says to change from Fahrenheit into Kelvin, we're going to move to Celsius and then to Kelvin, but between that, so would we still round for significant figures?
Excellent question. So we don't want to round until we get to the very end. Sometimes it won't make a difference. Other times it does, and I'll be emphasizing that later this morning. Good point. So the metric system, once you get your mind around it, is way easier than the English system. There's much less stuff to remember. It's just a really great pattern. We use scientific notation a lot in chemistry because we have very large numbers and very small numbers that are really inconvenient to express in decimal form. Avogadro's number is 6.022 with 20 zeros after it. That doesn't fit in the calculator, right? You should all have learned scientific notation in your prerequisite class. There's an appendix in your book, Appendix 1A, that's going to go over that if you need a refresher. So I'm not going to teach you scientific notation right now. The SI and the metric systems use prefix multipliers to change the size of units. I live in Reedley. I drive roughly 30 miles to come to class here. I measure that distance in miles, right? It would be crazy to tell in inches, right? If we look at a piece of paper, you know, how long is the paper? Well, it's 11 inches long. No, 11 inches. 11 inches long. We're not going to tell how long that is in miles, right? So it's convenient to use a unit that is similar in size to what you're measuring. You don't measure how much milk you have on hand in teaspoons. You measure in gallons, right? So we use units that are roughly the same size. We need lots of different units for this reason. In the metric system, instead of having these seemingly random arrangements like 12 inches in a foot and 3 feet in a yard, everything is based on powers of 10. And all the units use the same multipliers. So if you want to make a unit 1,000 times smaller, you use a milli prefix. Makes it 1,000 times smaller. You want to make it 1,000 times larger, you use the prefix kilo. So they're all powers of 10. So the example here, 1 kilometer. This prefix kilo means 1,000 or 10 to the 3. So 1 kilometer is 1,000 meters, or 10 to the 3rd meters. So reporting a measurement, we're going to choose a prefix multiplier, choose a unit that's similar in size to what we're measuring. So these are a lot of the metric prefixes. Some of these are on that list of material to memorize. There's going to be a quiz on Tuesday, right?